So I have the great pleasure now of introducing Dave Miller, and just reading through a short version of his bio. I think he'll tell us a great more of the background and to what he's done. It reads like the kind of ultimate MIT story, not only of technological contributions, but also of national service, which also very much characterizes MIT's contributions over many generations. Dave Miller is a former director of the Space Systems Laboratory and the Jerome Hunsaker Professor Post-Tenure in the Department of Air and Astro at MIT. He's played an engineering role in the development of space-based apertures. He's built and operated a dozen spaceflight experiments spanning shuttle, Mir, ISS, and free flyers. He was a member of the JWST Product Integrity Team and the vice chair and S&T chair of the Air Force Scientific Advisory Board. He served 2.5 years as NASA chief technologist at NASA headquarters in Washington, and 3 years as vice president and chief technology officer of the Aerospace Corporation. He's currently the chief technologist for the Astronomy and Fundamental Physics Directorate at NASA's Jet Propulsion Laboratory and an AIAA fellow and member of the National Academy of Engineering. And as impressive as that list is, it barely scratches the surface of what Dave has really done for this field, and we're now about to hear from that. So welcome, Dave. There.
Thank you. Now we check if all my preparations for my IT equipment actually worked. Yep, good. Well, thanks for inviting me here today. I understand it's a celebration of the Space Systems Lab, which is somewhat overdue, but better late than never. My passion throughout my career has been doing research, or technology research, and my other passion is flying experiments in space with students. So this story that I'm going to tell today is really a marriage of the two. It's how to create technology research laboratories in space that are not just useful to us, but actually to a wide variety of organizations worldwide. So that's the story I'm going to go with. This story starts with baby pictures, of course. So if you look at the upper left corner, you can tell that's the old picture because it's in black and white. That's me on the very left sitting on my mom's lap. I'm 6 months old. And this is the first meeting of the Society of Women Engineers in Pittsburgh, Pennsylvania. Yay, yay Pittsburgh. Where's the towel, you know? And it happened because my mom was the co-founder of the Society of Women Engineers in 1948 at Drexel University. And it became nationwide in 1950. Anyone a member of SWE? Okay, well, we need more. And I got interviewed by the national office for their 70th anniversary newsletter. It was about founding families. And they asked me a question: did you notice that your mom was different than your friends' moms? And I'd never thought about that. But I thought about it for a moment, and I said, really, yeah. Because my friends' moms were homemakers, hairdressers, grocery clerks, things like that. My mom worked with Admiral Rickover on the drivetrain for the Nautilus submarine, the first nuclear submarine in the world, I guess. She would build museums. She did renovations of old houses. She would keep me home from school to watch the Gemini and the Apollo launches. The school would call up, and she'd read them the riot act that I'm getting a better education at home. She bought us both motorcycles so we can go riding together. One day she said, get in my truck. She had the truck. And we're driving along, and I said, where are we going? She said, we're going to the airport. It's time you learn to fly. So that night, my dad comes home. I'm all excited, and I say, I'm going to go learn to fly. And he said, yeah, this is a good time for you to learn how to pay for it. So that sort of suppressed things for a little while, but not forever. So that was good. She said, you have to go to MIT, and you have to go to AeroAstro because of their role in Apollo. She would write about space travel, but she was just born too early for that. So I went to MIT, AeroAstro, got my bachelor's, master's, and doctorate. And then when I finished up, I had 3 job offers. One was faculty at Cornell, one was at JPL, and one was research staff at MIT. And I thought, I want to work on space hardware. So nothing against Cornell, but I said, that's not going to Cornell. I figured if I went to JPL, I'd be a small fish in a big pond, and that really wasn't what I wanted to do. But Ed Crawley in Aeroastro had recently won a shuttle flight experiment. And I said, I could be a big fish in a small pond on that one. So I accepted that research position. That really sort of, I felt like fired my career out of a cannon. And it's nothing like in your first few years of doing after your education, of working with the astronauts and the shuttle program and the research and the industrial partners and all of that, to really be exasperating and stressful, but very rewarding to do. So, so that really launched my career. Ed Crawley had given me 2 pieces of advice. One was, whenever opportunity knocks, say yes, even if it's very intimidating. I said no to a couple things, and I stopped doing that. I started saying yes, and that was very rewarding. The other thing he suggested was you should reinvent yourself several times through your career. So I did. So I spent a lot of my time up here at MIT, and I still do. I still have students, the graduate students, but I joined the Air Force Scientific Advisory Board. I was there for 4.5 years. I got interviewed for Chief Scientist of the Air Force, didn't get that job. That's all right, keep trying. But I got the NASA Chief Technologist position, and then I got the aerospace position, and now I'm at JPL where it doesn't snow. So that's great. And the one thing that I find very key along this process since I've left MIT is that I keep my grad students. I currently have 2 PhDs and 2 master's students, and that's solving technical problems with the best workforce in the world. Really keeps me centered and able to deal with the bureaucracy that these other career paths have to endure. So. Okay, so at the time I became faculty member, Ed Crawley was department head. He had come up with this conceive, design, implement, operate context for a undergraduate education. And I really embraced that because I thought that's what I want to do. I want to get hardware in space, but you got to start somewhere. You got to start with formulation, which is really conceive, and you got to test it and build it out on the ground, and then you've got to figure out how to get it launched and then operate it on orbit. So my research was really guided by this. On the conceive side, did a lot of integrated multiphysics modeling, a lot of architectural trade space analysis, and actually started a unique 3-semester design build class where we could try to build things. And often we learned what not to do, but we would also learn what to do. And then we would bring that into the graduate program and up onto orbit. On my design work, I had really mostly studied dynamics and controls. But I didn't really want to dive deep into the control side. What I wanted to do was see how controls could take advantage of the unique dynamic aspects of the problem to which we're applying it. So I'll show you some of that as we go, but here's a listing of the various research threads in the Space Systems Lab. From vibration suppression for space telescopes, all of this really focuses on space telescopes. Adaptive optics, machine vision, formation flight, things like that. And then I want to mature them through test beds, both on the ground and on orbit. And because there's nothing like an experiment to tell you what you forgot in the theory. So that's a real awakening to go. The model said it should work, and why isn't it working? So, and the other thing is for the facilities that go up to station or shuttle, we wanted to really operate them like they were a research laboratory on the ground, that there's really no distinction between it. And I'll show you some of that later, but I think a great analogy is the wind tunnel. A wind tunnel is where you take a formative technology, we don't quite know what the final form is going to be, and we test it in an authentic environment, in that case a wind. On orbit, it's microgravity. And we want to test it under nominal and, more importantly, off-nominal conditions, and without doing harm to the test article, the operator, or the facility. For our payloads, the underlying requirement was do no harm when you go to space. So the reason why it's more importantly is if it works under nominal conditions, that's good. That's necessary, but it's not sufficient. You need to know how far away from the cliff you actually are. So by moving it to the point of the technology breaking, not the hardware breaking, but the technology breaking, that tells you how far you are from the cliff and how to extend that distance. And that's why you want to do these kind of tests. Okay, so as the title said, this is 30 years of the Space Systems Lab, so I'm going to go by decades, but I'm actually going to start in the decade before the Space Systems Lab started. This is what I call the shuttle era for our lab. It was the Space Engineering Research Center. It was 1988 to 95, and we flew the first shuttle experiment that we flew was MODE. We flew that in 1991. Stands for Mid-Deck Zero Gravity Dynamics Experiment. We designed this to be very modular in the sense that there were pieces that were your generic lab equipment, or like your data analyzer, your storage media, your power amplifiers, your signal conditioners, and they were all located in one box, and we had that in a mid-deck locker. You could just put it there. But on the front, there was an interface that you could attach different types of payloads to it, different kinds of test articles that you could test. In this case, we were doing fluid slosh on the first flight. We were doing nonlinear truss structure dynamics and microgravity on that flight, and it went well. But much to my surprise, the flight programs kept coming. So in 1994, we had the opportunity to refly the hardware, but add additional things to test on it. So Professor Newman had just joined the department around that time, and we said, we have some hardware and it's all qualified. If we just build the things you want to build, we can put it on and we can fly. And these are the dynamic load sensors, which are 6 degree of freedom sort of load cells mounted on foot loops and handholds, so that we could get a measure of the most unknown disturbance source on station, and that is the crew's motion, and how much Mike Fink would disturb that lovely microgravity environment up there. So we flew that, and then before we got that off the ground, NASA approached us and said, hey, can you add active controls to the problem? We said, sure. So that became the mid-deck active control experiment. We tested, that's shown on the figure on the right here. That went up on the shuttle in 1995, and we did robust and adaptive control on that, but we also did verification through integrated modeling. And I put a star here because this is something I want to talk about in more detail, because little did we know that in 1995, when we flew this mission, it would be the pathfinder for how we verified that the James Webb Space Telescope would work prior to launching it. So the idea of I looked up one of our old journal articles and saw what the objective of MACE was, and it was to develop tools for spacecraft that cannot be tested on the ground in a sufficiently realistic on-orbit environment. And then those tools should allow us to have confidence in the eventual on-orbit performance. So that's what the verification process is for flight programs. We had built test articles for the shuttle that changed their dynamics between 1G and 0G. Some we couldn't even test in 1G because it would have broken. And then the process we used here is this integrated modeling bullet here. We built a 1G model that had multiple physics, in this case structural statics, dynamics, sensor and actuator dynamics, controls, algorithms, and time delays, and violin modes, and suspension cables, and gravity sag, and all these things that represented the 1G test environment. And then we did tests. And these were we designed controllers and implement that, and nothing like a control system going unstable to give you a sign that something's wrong, and you forgot to include something in your theory. And then once we refined that process, we took the difference between the data and the 1G model predictions and created an uncertainty model. We propagated that into 0G and then applied it to a 0G model and designed controllers, which we implemented on orbit. We also had the opportunity that I think was non-existent at the time for shuttle to bring down data, redesign controllers, send it back up in the morning mail, and implement it again over the course of 2 weeks. I think we did that like 5 times during the mission. So what does that have to do with James Webb? Well, here's James Webb in the big A chamber down at Johnson Space Center, going through its sort of all-up testing. So to give you a little bit of indication of what's what, there's the mirror. That's probably the obvious part. Here are all these suspension cables, because it's 1G, you got to lift it off the floor. There's a 1 hertz isolator that goes between the bus of James Webb, the spacecraft bus, and the telescope. 1 hertz isolators and 1G sag about 10 centimeters. That would have ripped the isolator apart. So what they had to do is mechanically short it. This is also a nested thermal chamber. So what you're seeing here is a liquid helium wall, and outside of that is a liquid nitrogen wall that keeps the liquid helium liquid. And, but the temperature environment was not really what it was going to see up at Earth's Sun L2. So that was a little different as well. So what James Webb program did is they developed a STOP model. It stands for Structures, Thermal, Optical Performance. Some of those physics are different than what we did in MACE, but the integration of it was the same thing we did in MACE. And that model was built by my graduate student who worked on MACE. He built it for NASA Goddard, and that's the process we used. The same thing, 1G model, the 1G data, get an uncertainty model, apply that to the 0G, model, and then we would predict whether James Webb was still in spec. It was, we launched. The other thing is I sort of bookended this because, as Dave mentioned, I was on the product integrity team for James Webb, and my role was to advise on dynamics modeling and testing, how you would test the dynamics of James Webb. And so we sort of had both ends of the program there, and that was great to see the results of MACE be applied. So what I'm going to show here is a movie from the shuttle, and hopefully the sound will be good. Not too loud, not too soft.
Okay, Joey, welcome aboard. We've got about a 6-minute video to show you here, and we'll bring you back on the flight deck for a little bit at the end of it. Here we are on the mid-deck, and I'll show you just a little bit of the assembly of the MBP, or multi-body platform, that is the main attraction of the MACE, or Mid-Deck Active Control experiment, that we ran on Endeavour here for the last 16 days almost. And here I'm assembling 2 of the struts and an electronic data connector to one of 3 nodes. The node in the middle has 3 rate gyro assemblies connected to it, as you can see there.
Those are also
Translated over to the ESM, or Experiment Support Module, which is housed in one of the lockers, and also includes the disk drive where the data is stored. And the data gets across on the white umbilical that you can see there. Also in the frame right now is the KISS box that we've been using all along for getting data to and from the ground. Is that blue box on the locker that you see. The MVP consists of 4 struts, the 3 nodes, 3 rate gyros that are mounted orthogonally, and then at either end there's a 2-axis gimbal assembly, and the end behind my head there is the secondary or disturbance end, and the other end on the left of the screen is the primary end, or the end that we're trying to control. And the whole idea here is to put a disturbance end to the end that I have my hand on there that actually shakes the whole structure and will in fact disturb the performance of the primary end. And the idea is through active support or active control of the assembly on the left to actually allow that or enable that gimbal to point very accurately at a single point in space. And this would simulate a spacecraft that had, say, a scanning device at one end and a pointing device requiring great accuracy at the other end. Here we're starting a run that has a disturbance going in at the far end, and we'll be trying to control the left side here. And the control has just kicked in, and we'll give you a couple of close-up views and give you an idea of what this really looks like. And the vast majority of the runs that we ran were a lot like this. We'll show you a few that didn't work out like this too. This is the disturbance end, the secondary gimbal, and you can see that shaking the whole assembly. And in fact, at the primary end, which is not being driven, just being disturbed by the disturbance end, you can see it shaking here, and then the control will kick in right there, and you can see that it settles down very, very nicely. And while we were doing this, we were uplinking new controllers, downlinking the data, and the folks at MIT were looking at that. And they were writing better controllers, and the performance of these controllers got better and better as the flight went on. Here I'm mounting a laser pen to the primary end so that we can demonstrate for you just how remarkable this active control is of this device. Here the disturbance has gone in, and you can see the laser spot against the sleep station. And the control goes in right there and very accurately points the primary end. Now, not every single controller worked this way. Some of them performed, and like I said, the vast majority of them performed very well and got better as the flight went along. But there were some, like in this case, you can see the spot against the sleep station is being driven at a high frequency and is actually being driven off the target. And this is not the kind of control that you'd like to see. But it does demonstrate that if you're not careful, you can actually make the problem worse by designing a poor controller. And you can make it bad enough that it actually completely over-controls the structure as you see here.
He has to land the shuttle 2 days later, so we're a little nervous here.
We had several different configurations of the multi-body platform. Here's configuration 1, and it's actually the configuration that we ran the majority of our runs in. And this is another one of those controllers that did not perform as well as you'd like, but on the other hand, we were learning an awful lot from these controllers that went into these divergent states. And then the final configuration that we had was actually the most fun. It was configuration 2, the original configuration that we showed you, plus what we called flex appendages, which simulated, say, solar arrays on a space station or a spacecraft of some type. And you can see those at the orbiter's z-axis, along the orbiter's z-axis in the middeck. And here's another one of the controllers that actually drove the whole assembly into an over-control or out-of-control situation. And the amount of travel that this particular vehicle would have taken was actually limited by the tethers that you see there, or it would have gone flying on into the overhead of the launch face, forward of the assembly.
So I want to remind you of two things. This was all done by graduate students in an era where universities and graduate students really didn't get the chance to fly things. So I think, this was a millennium ago, remember? This is in the 90s. And the second thing I want to remind you of is the wind tunnel analogy. Don't harm the test article. Don't harm the operator. I'm looking at the astronaut. And don't harm the facility. Yet you have to push it to failure. So that was a tricky sort of design constraint. So, and it worked. So I'm going to fast forward to the next decade. This started with the founding of the SSL, Space Systems Lab, and the flight opportunities just kept coming. We got the opportunity to fly 2 different missions up on the Mir space station. This was part of the Russian-U.S. collaboration and preparation for ISS. And so the mode hardware here, we built on that. We flew what was called, with Professor Newman, the EDLS for extended duration, enhanced dynamic load sensors, thank you. And the nice thing there is, I remember we were doing it on the shuttle where we might only had 2 weeks or something, and someone said, you should see how the Russians fly, especially how they adapt over time. So, but you need a longer time constant to see that. We also flew a version of mode up to do the Mazu-Mizdi experiment. Looking for Javier, did I get that right? And that was to get an acceleration survey of the Mir space station to understand what its modes were and things like that. So that wasn't with our lab, but the idea of the modular design allowed us to sort of get these things flown fast and less expensively. We also got the opportunity to refly MACE, and this went up on the space station for expeditions 1 and 2. So this is Bill Shepard, who's a graduate of course 2 here at MIT, mechanical engineering. And I think the space station consisted of 2 modules at that time, maybe, yeah. So it was pretty crowded in there. and I'll show you some about that. It's also the year when we started this multi-semester capstone class, where we wanted to give juniors and seniors the experience of the full life cycle, let them come up with a concept and then build it and then go operate it someplace. And after, the first one was called Spheres, the first class project. And right after we finished the class, we got the opportunity to build it for Space Station. And this was one of the flight units, and it has a little expansion port here that would allow us to, in the future, add other payloads. The thing is, we were packed onto the shuttle, I think it was STS-116, which was supposed to be the mission that was right after the last flight of Columbia. So that caused the whole fleet to be grounded, and part of that we had to figure out another way to get up to station. So I'm going to talk about here a little bit about the capstone class and our MACE reflight. So this is actually why it sort of looks distorted here. Is this is out of an IMAX film, and this is Susan Helms, who was on Expedition 2. And nice little clip. We had modified Spheres to add more flexible appendages here so we could give it more nonlinear behavior. We also modified the software to allow neural nets, and we teamed with the University of Michigan on this and with AFRL. And this was the first crew interactive experiment on Space Station, so thank you, all you taxpayers out there. We really appreciate that. Oh, that's MACE. Sorry, this is MACE reflown. Yeah, I got Spheres on the brain a lot. That's coming up.
The MACE experiment is how Susan entertained herself on the weekend.
Yeah, I really liked working with this experiment. I mean, it was like playing with a big toy. It had moving parts and a brain. When you launch a satellite into space, the control system is the designer's best guess of how it should control its own sensors and appendages. This experiment was trying to understand how you could design a control system to teach itself to work better.
So as I said, this is also the decade where we started the design build capstone class. It started as a 3-semester class, and then it shrunk to a 2-semester. But I already mentioned Spheres here. That was our first project, and David Newman and I co-taught the class. I hadn't taught a class before, so thank you for that. I listed some of the follow-on impacts. It did go up to station. It was on station for 14 years. It was the first IVA free flyer, and a number of other nations have copied us now. Well, we copied ourselves with the Astrobees that are up on station now. The Japanese, Simon, and there's one from ESA, and I think the Russians have been talking about it. So we went first, and I guess it's popular, so that's good. It also, some of the work we did impacted the Cassini mission. Some software got loaded from Spheres loaded onto Cassini. Makes you nervous when your graduate students are writing software for a mission around Saturn. Our fluid slosh work impacted Delta IV Heavy cruise dynamics during its GTO out to GTO transfer. And there's a big STEM impact here as well. 2 years later, we did a multi-aperture Fizeau interferometer testbed on an air bearing with control to sort of point the stage control from ACS up to optical control. And one of our panel members, Soonjo Chung here, is Professor Soonjo Chung here, was our TA, and that was a great success. We then went to one of these crazy ideas called propellantless formation flight, and the way we did it was using electromagnetic forces and torques between vehicles to be able to do that. That went to ISS, and 3 companies have been built around this idea. Fortunately, none of them do I have any ownership interest in. We then built a modular spacecraft with docking ports so we could reconfigure them. That went to Space Station. Our docking ports went to JPL and Lockheed. We built a modular rover for extreme terrain access, and the vision system here went up to ISS. We also built 2 different orbital transfer vehicles. Then we partnered with EAPS, or Course 12, Earth, Atmospheric, and Planetary Sciences, to do a collaborative class. This was with Professor Sarah Seeger, to build something she called ExoplanetSat, which would be the first sort of 3U CubeSat that had sub-arc second pointing accuracy. When we finished the class and the graduate students sort of revved the design, JPL then hired our graduate students, renamed it to Asteria, and it's been flying for a while now. We also built an instrument called the Regolith X-ray imaging spectrometer, which went on the OSIRIS-REx mission to Bennu, and since it's bolted in place, is that right, Dr. Masterson? It's now heading on its way to asteroid Apophis. And then our last project that I was involved in was a spinning aperture telescope, a rectangular telescope that you spin to fill in the image plane. And the students chose to name it after our president of MIT at the time. So the first day of class, don't worry, this clip is less than 30 seconds, it's okay. The first day of class, actually before the first day of class, Earl Merman told me, you know, so you want to do this crazy class of trying to, you know, do this life cycle experience? And I said yes, and he said, well, you know, this is the smallest junior class we've had in a long time. You need to get a critical mass of students involved in the class. So I had an idea. I think Dave and I had the ideas. We're going to bribe them. So we sent out an email to the juniors. We promised, if you join this class, you're going to fly on the zero gravity plane. So we got enough students. And so on the first day of class, you probably remember this movie, but we forwarded to this clip, and what you're going to see here, we told them we want 3 of these, we want them in station, and no laser beams, please. I think you get the idea. So we started to work. They all booed when I hit the stop button on the VHS tape player. But so we did this, and we got up on the KC-135.
When I first came to MIT, I had no clue that I would be doing anything as cool as this. Never would have thought that I would be doing this, ever.
It's been definitely the culminating experience of MIT for me.
This opportunity came up, and it was just like, wow, I want to do this. This is what I want to do.
It's a completely different, real attitude to learning about aerospace engineering.
It's giving you a taste of the real world, I guess, before you get a chance to get out there.
The Spheres project is really sort of 2 things rolled into one. One, it's part of a research program that the Space Systems Lab is running. Second, it's also an academic
I've lost my hair, but David looks the same, so I don't know what's going on.
Undergrads, systems engineering.
We're good.
We've been teaching them the design process, and it manifests itself into an actual flight hardware, and the specific hardware for Spheres is actually formation flying satellites.
We basically interviewed industry and we said, what is it you want to see in your new hirees? And they said, we would like to see hirees that have the full life cycle experience in developing an aerospace product.
We're trying to make our conceive, design, implement, and operate the context of an engineering education.
So we came up with this course, which is really a 3-semester course, and started basically with a clean sheet of paper, where we gave them a problem, something to build, gave them some requirements, and they took it from there, built the thing, and are now operating that facility in NASA's zero-G aircraft.
The students were presented with a basic concept and allowed to run with it in their own pursuits.
The concept is that instead of building large, expensive satellites, we can make them cheaper by perhaps building smaller ones and coordinating their activities. One of the key uses of these formation flight technologies is for future space telescopes.
You could have autonomous satellites spaced far apart, and the application there would be interferometry.
Interferometry, basically, instead of having a large mirror, takes 2 smaller mirrors and moves them further apart. Now the angular acuity on the sky is no longer determined by these diameters, but is determined by this separation.
Compared to the Great Hubble telescope, that's very large, you can now think of smaller satellites, but getting the same optical resolution.
We can take smaller, less expensive mirrors. Instead of the 2.5-meter diameter of Hubble, move them out a kilometer. You can imagine the kind of fine detail in the sky we could start to see. On the KC-135, the real goal is to see if we can predict how our algorithms will work in an environment other than that in which we designed them. So we can't do that in the lab. We can't test in zero-G, but we can design controllers, go up on the KC-135, see how they behave in zero-G, and see how our predictive capability is.
They did pretty much what they were supposed to do. You lift it up and let go, and it stabilizes itself. So we demonstrated that, which was one of the goals of the flights.
I think that we got some good data on both what the sphere is doing and on what the plane is doing, because the plane does some pretty extreme stuff, and that what the plane does also affects how our experiment works. I was telling somebody the other day that if we're in a group walking somewhere where I have images of the right stuff floating in the back of my mind, and everybody I tell about the project, their jaws just drop, and they say, wow, only at MIT, and that's the way I feel.
And that is not the Brad Pitt, but thank you. So the second decade, things really kept going. Actually, it was a busy decade, and it was almost too busy. But we finally got spheres up through a combination. We launched on almost every launch vehicle there is in the world's fleet. We launched on the Japanese HTV, the European ATV, the Russian Soyuz, on Soyuz. They don't tend to carry payloads. And Progress vehicles, and then shuttle once it became operational again. And we actually, because of that expansion port, we sent up a lot of different payloads. Some were from the Capstone class, and others were not. So we did proximity operations just because we're operating in an aluminum can. We cannot go more than 3 meters apart, but there's a lot of interesting things you can do. We gave it eyes, stereo vision, and I'll show you a little bit about that. We put up slosh tanks at, this is a project that was supported by Kennedy Space Center's launch services providers because they were having some issues with the Delta IV Heavy fuel stabilization. We were also put up docking ports because we wanted to work on in-space assembly. And this was more of our sort of our bat belt or whatever you want to call it, so you could put robotic arms and docking ports and multiple payloads on at once. And here is our electromagnetic formation flight vehicle. You might remember it had rings on it. Well, this is actually called rings. It can not only control their relative motion via electromagnetic forces, but you could also do wireless power transfer between them like you do with your phone when you put it on a recharging puck. So I'm going to show you some things about vertigo and rings. That's what the asterisk means, and our UDPs, which are universal docking ports and things like that. We also, one day, Dr. Sanzoterio came into my office and said he'd been talking to astronaut Greg Chamitoff, who had operated spheres up on station, and said, we have a plan. I'm like, uh-oh. And they said, the way you do safety we do safety with spheres is that we make sure that software is not a safety control. So, because that's how the technology is instantiated, and we don't want to have to go through NASA safety every time we change software. So, Greg Chamitoff had said, so anyone can program these. I'm like, yeah, where are you going with this? And so he said, let's run a competition, a robotics competition on orbit, which would be the first one run off the planet. So we called it Zero Robotics because First Robotics already had a bit of a brand, and we wanted to get ahead of them in the Yellow Pages, if anyone remembers Yellow Pages. But I'll show you a little bit of that as well. But one of the things I really wanted to do was support robotic assembly. Because if you're going to do robotic assembly, especially of telescopes, you're going to have a lot of pieces you got to move around. If you do that outside and you lose some pieces, you might be asked to testify to Congress. If you lose them inside, they bounce off the wall and the astronaut hits the pause button and we can test again. So it gives you that time to iterate and take a little risk. So here's a concept for doing in-space assembly, and it uses our electromagnetic formation flight, or EMFF, which stands for oomph. We thought that was kind of cute. So you get a rocket, you write your name on it, you stack your mirror segments like dishes in a kitchen cabinet. You get one EMFF vehicle up there, and you have another one mounted at the bottom here. So it's magnetically pushing and torquing against the one at the top. You use your UDPs or your docking ports to come in and grab a segment, and you bring that out with hopefully not scraping the mirror. So magnetic forces, opposites attract. If this is a dipole magnet, opposites attract. The same type of poles repel, but if you move them perpendicular, they'll shear, and you can get all 6 relative degrees of freedom. And so it's propellantless propulsion, but it's all staying within close proximity, which is what EMFF needs. And it's all the relative degrees of freedom that matter. So for you telescope people, you really don't want a flat mirror. You'd like it to be a little curved, but we didn't convey that to the animator here. The last thing you do is you grab the secondary mirror and jettison that truss and hope it doesn't come back to hit you. And then you position that secondary mirror up in front of the telescope and you magnetically trap it there. And now you get rid of the, if you remember that secondary support tower you saw for James Webb, the diffraction effects of that are not there. Of course, there are other challenges here, but it's possible. So I'm going to show you how for that EMFF, which was a class project, the pathway it took to space station. So we got the class together. This is what they built. Looks kind of mean. That's an open jug of liquid nitrogen. Be careful. It froze all the water out of the atmosphere of our lab. We got 10 turns of high temperature superconductor in each of those 2 coils. And the one in the back is bolted down and it's got 100 amps. So that's 10,000 amp turns. And the one here, we're putting 100 amps through it. It's a handful of D-cell batteries. It's amazing stuff. And here we're just doing open loop. You can see the nitrogen boil off coming down. That's not a good trade with propellant, but we actually developed a cryogenic heat pipe that could do that with no consumables. So it can push away as well. Those are 100-pound vehicles, and it's pretty agile here. I don't know if you saw in the last frame, the student was wearing his safety goggles up on his forehead. He's more interested in fashion than safety, but oh, there we go. Yeah. We had to give it an umbrella because it started raining on our electronics. Probably a problem we wouldn't have in space. But yeah, and when we change the current, we just recharge the D-cell batteries, and then we pump up the coils again. Shear is the interesting one. That's where you put the magnetic dipoles perpendicular. So in this case, the dipole of this vehicle is across the table, and we had to commutate it. So it's the current's in that coil, that edge on coil, then that edge on coil, just like a DC motor would work. And the reason it has to rotate is because it's all internal. Remember this? Channel your undergraduate physics class. It's all internal forces and torques. But here, we've induced angular momentum into the array. And angular momentum has to be conserved, so it goes into the spin of that vehicle. So now we turn on a reaction wheel to absorb that angular momentum so that the vehicle's spin didn't have to do it. That's a math error. It's nice to show the physical instantiation of a math error to the class. They didn't design the reaction wheel to have enough torque to prevent it from rotating. We also always run the camera, always video, because you never know when your last test is going to be, because the smoke came out or whatever. So video hides a lot of faults. So then the class graduated, and then we brought it into the graduate program, learned a lot, redesigned the vehicles, and you'll notice they look a lot slimmer now. We added active control to them. We used the Spheres measurement system, which uses ultrasonics synchronized by infrared. And now this one's under active control. That one's bolted down, 10,000 amp turns in that coil. And so now he's going to push it forward. It puts current into this face-on coil to repel, comes back, but then it has to reverse that current in order to stop its drift away. You can see how anxious the students are. It's probably the 100th take of this, but especially this guy's grip right there. But I can imagine the silence in the room. Then shear, this is the one where you make the dipoles perpendicular. We do have a reaction wheel that's better designed. Could have used a little tuning, but it's bringing it back to the objective position in the center of the table. And he's very happy. he's sort of questioning things. And then they're as strong as reaction wheels. These are pretty powerful. So I'll cut that. So now we got to a point where we sort of had all the pieces coming together for this telescope robotic assembly lab up on station. So we had EMFF, and you saw the photo of it on station. We also needed things, here's just a photo of the team, but they deserve all the credit. We might need to be able to dock and undock, and if you dock with something you don't know its properties well, you might have to do a system identification to learn them. So we did some of that up in station. You know, for 14 years, this was really a lab that we used almost weekly up on space station. And you might need to, it could be a crowded workspace. You might need to be able to do collision avoidance. So here we command the spheres to go to the vertices of an equilateral triangle and then go down the bisectors, and they automatically detect they're about to collide. So they have to replan how they're going to go around. And you know, when you do that dance on a sidewalk where you're going left, right, trying to pass the person coming the other direction, this is a 3D version of that dance. And then you probably want to have eyes on the construction site, so we gave it eyes. And here we're actually doing a 2-vehicle inspection of a tumbling object here. One of the interesting things is our propellant tanks on these spheres have liquid CO2 as our propellant. That's a whole nother story. So this is a nutating spin. One of my grad students saw how that nutation affect the pole hode. Everyone remembers the pole hode, right? Right? Yeah, thank you. So we could see that the pole hode, which for Euler dynamics should stay constant, was oscillating. And that means it's not a rigid body, it's flexible, it's a fluid. He was able to estimate the amount of fluid left in the gas tank just by watching its motion. So now we had all the pieces together, and then we moved to another decade. We actually didn't get that test bed up there. The spheres, after 14 years, were really running out of gas, literally. But the thrusters things were wearing out. So the third decade here of SSL still had a lot of action going on. We got the opportunity to build REXIS, Regolith X-ray Imaging Spectrometer, on the OSIRIS-REx mission. I'll show you more about that. You could ask, what do we have to do with Perseverance rover landing? A lot, because the JPL entry, descent, and landing team for Perseverance was comprised by a lot of SSL grads, and I'm going to show you that. And then we also did star shade trajectory work. This is the next great observatory in astrophysics at NASA, and the idea is to be able to get spectra of Earth-like planets around nearby stars. But to do that, you got to block the light from that star because it's 10 billion times brighter. So an idea to do that is to put a star shade in front of that star, and it has to be about 10,000 kilometers ahead of the telescope. It's kind of what happens when the moon gets in front of the sun and you do a solar eclipse. This is just sort of a human-made eclipse. But you can imagine at 10,000 kilometers in advance, you want to look at other stars, you got to move this thing around the sky to block other stars. And NASA had looked at how much delta V and fuel they needed to do that. They assumed the gravitational dynamics in Earth's sun L2, which is the 3-body problem, are trivial and we can ignore them. So they did an estimate, but 2 of my grad students came in, modeled the whole 3-body dynamics, and developed the optimal trajectories. And they were able to save 25% of the delta V and 40% of the fuel in the mission. And they really wowed JPL on that. Maybe embarrassed them a little. That's good. So I'm going to show you about zero robotics here, but I'm going to start with REXIS and Perseverance.
Fenway Park may be the home of Boston's most beloved team, but another is about to steal some headlines. This group consists of students from MIT and Harvard who are getting the chance to build an instrument that will help NASA's OSIRIS-REx spacecraft explore the asteroid Bennu. This group of student scientists are building REXIS, the Regolith X-ray Imaging Spectrometer. Its purpose is to collect and image X-rays coming from the asteroid to determine its elemental makeup and distribution of elements across the surface. Each student has a unique task on the project.
I get to practice being a thermal engineer and honing my thermal engineering skills.
My role is to work with the solar X-ray monitor as well as some of the avionics side.
On a daily basis, I write test plans and assembly procedures.
I work on the Rex's avionics system, and what that is the electronics that take the X-ray signals from the asteroid and make sure that they get back to the ground for the scientists to process.
As a systems engineer, I'm responsible for making sure that all the different technical disciplines come together. Thermal, structures, avionics, software, they all come together to make one working instrument that meets our science requirements.
And making sure everything stays in check is Becky Masterson, the Rex's instrument manager and the group's faculty supervisor.
Rexus is an interesting instrument on OSIRIS-REx in that we're a student collaboration experiment. The goal here is to educate students. And the Rexus project has been a fantastic way, to do that. Both undergrads and graduates go through this project and get a real live view into what it is to build space hardware.
And building Rexus is an intense process with strict contamination controls and elaborate software and hardware testing. And there's one thing every college student can relate to: note-taking.
On Rexus, the reason that we have such careful procedures and note-taking is that in the future, if during an environmental test or other integration activity we notice an anomaly, we can try to trace it back to a root cause. And if you have detailed notes, it's easier to go back and figure out what may have happened during assembly.
So what's the biggest challenge in building Rexus? The answer may surprise you.
Having students involved in Rexus has been a wonderful experience. It's been an adventure. One of the difficulties of it is that students are always coming and going. So you get a student in, they're here for a 2 years master's, and they learn a lot, and they're doing great, and then they're gone.
So working on Rexus is a bit like riding the T in Boston. Some students going outbound, some coming inbound, but all are getting the same collective learning experience.
So the biggest thing I've learned while working on Rexus is really that instruments like this and spacecraft like OSIRIS-REx are very, very complex. There's a lot of dependencies, a lot of requirements, a lot of relationships, a lot of design decisions that all impact one another.
Rexus provides a hands-on experience for students to build flight hardware for a NASA mission. And that's incredibly rare, that as a student you can build something that's going to fly in interplanetary space. So this is like a lead-in to a future career in NASA, a future career in rocket science.
That's exciting for me. I get a kick out of thinking that these pieces that I'm touching and this assembly that I'm building is actually what's going to fly in space. So I think that's pretty cool.
And between Fenway and Boston's other attractions, students must feel completely spoiled with their social life, right?
Yeah, well, I don't go out much. I don't know, was there much to say? Usually I have to work on Rexus.
So, while it's true these students may strike out trying to find that perfect balance between schoolwork, a social life, and working on Rexus, as scientists they are hitting a home run for the OSIRIS-REx team.
So I'm running a little long here. So this is a photo of a bunch of graduate students that graduated from the Space Systems Lab, and they're the core of the Entry, Descent, and Landing team for Perseverance at JPL. Do I have 10 more minutes? Okay, then we'll show you. The nice thing is this is all SSL students. One is a social member of the SSL, but they put this video together about a month before the landing. That's confidence. Oops, hold on.
Nothing can be taken for granted when you get to Mars. There's a lot of things we just don't know.
Space always has a way of throwing us curveballs and surprising us.
I mean, until we get the data that says we're on the ground safely, I'm going to be worried that we're not going to make it.
Entry, Descent, and Landing is often referred to as the 7 minutes of terror because it takes about 7 minutes to get from the top of the atmosphere of Mars to the ground safely.
The spacecraft has to do all of this by itself.
There are many things that have to go right to get Perseverance onto the ground safely.
There's a lot counting on this. This is the first leg of our sample return relay race. There's a lot of work on the line.
Starting about 10 minutes before atmospheric entry, we get rid of really the spacecraft part of the rover that's been supporting us.
We come screaming in to the Martian atmosphere at 12 to 13,000 miles per hour.
And the heat shield is what dissipates all that initial energy through friction.
The vehicle will continue actually flying itself through the atmosphere. It's sort of like a transforming vehicle that went from a spacecraft and now it's kind of like an aircraft actively guiding itself.
When we're going slow enough, we deploy a parachute.
It's the biggest supersonic parachute we've ever sent to another planet. It's critical for slowing down the vehicle.
Perseverance's entry, descent, and landing borrows heavily from that of Curiosity.
But fundamentally, Perseverance is a different rover. She's bigger, she has different instruments.
We've added a lot of smarts on the inside to make it more capable so that it can deal with the landing site that we've given.
The science team identified Jezero Crater as basically an ancient lake bed and one of the most promising places to look for evidence of ancient microbial life and to collect samples for future return to Earth. The problem is it's a much more hazardous place to land.
You look at Jezero, all you see is danger. How do we go to a site that we never thought was safe enough to go to before? So the heat shield, which has protected us all the way through entry, is no longer necessary. We need to get that off so that we can actually see the ground. And we can see the ground in a couple different ways.
Perseverance will be the first mission to use terrain relative navigation. So while it's descending on the parachute, it will actually be taking images of the surface of Mars and determining where to go based on what it sees. This is finally like landing with your eyes open. Having this new technology really allows Perseverance to land in much more challenging terrain than Curiosity or any previous Mars mission could. Amongst the rocks and the craters and the cliffs, these things are hazardous to the rover, but these are the things that are interesting to the scientists.
Once Perseverance has figured out where she is, we jettison the back shell and parachute and light up our rockets. Those rockets help us steer to a safe landing spot that's nearby.
That descent stage takes us all the way down to about 20 meters off the ground.
That's when we start the sky crane maneuver. Once the rover has hit the ground, the descent stage will cut loose from the rover and fly away to a safe distance. Surviving that 7 minutes is really just the beginning for Perseverance. Its job, right, being the first leg of sample return, to go look for those signs of past life on Mars. All that can't start until we get Perseverance safely to the ground. And then that's when the real mission begins.
So I was a little bit hurt that I taught them how to build telescopes and they go land rovers on Mars. But I liked that, so I changed my mind and said, I hope I taught them how to think. So that was good. And actually, 3 of my women graduate students were leaders, well, still are, leaders on 3 major telescopes that were very high tech. So at least it stuck some places. So I'm going to go back to Zero Robotics here, and as this was happening, this was Dr. Sanzotero's brainchild. As this was happening, Nat Geo got wind of what we were doing, and they wanted to make a movie. This is the trailer, and I apologize if I cry in this, but.
I want to go to space.
You want to go to space?
Yeah.
Oh, okay. This is the first time I'm hearing you say that.
Your mission is to program satellites inside the International Space Station.
And liftoff.
That is the space race right now.
And it's going to take every single one of you to make sure that our code is one of the best in the nation.
Robotics teams have been working in a worldwide challenge, using coding skills to see who can do it best.
For the Spheres experiment that's about to take place on the space station.
En inglés es Spheres, que es un GPS porque lo quieren poner en Mars cuando vayan.
You can dream whatever you want, and if you can work together very well, you'll fly straight to the moon.
We're gonna win this space race, okay?
My goal is to become a marine biologist one day. The water's just like zero gravity, close as you can get.
If you even reach space, you'll be like, oh, we're the champions and stuff.
Esa es la palabra NASA. ¿Di NASA?
NASA.
Se llama Steve Smith, es un astronauta.
The early years are the crucial years for them to get exposure to different opportunities and to find out where their passion is.
This is a robotics competition. Which of your team's code will it be?
I think
something that's in space that we're programming on Earth. That's like kind of crazy for me.
Let this be the start of a journey, a lifelong journey of learning.
Whenever people say the sky is the limit, I just think that they're wrong. There's much more ahead of them.
T-minus 10 seconds.
9, 8, 7, 6, 5, 4, 3, 2, 1.
Good luck to all of the contestants, and let the games begin.
So I want to close with thanking so many people that helped. In white are all the grad students that I could remember, but I'm sure Becky and Alvar will find some that I missed. The M means masters, the D means doctorate. 50 doctorates, 94 masters, and I'm not retiring, we're still going. But I really want to thank the people on the right for Alvar, who created spheres and Zero Robotics. Becky, who led the team to fly the furthest student-built experiment to AU. Marilyn, who made sure that we grew up from kids to being responsible adults. Paul Bauer, who taught things that you can't learn in a classroom. And one day he actually said we can duct tape down the circuit breaker on a high power amplifier, and it worked. Dave Robertson, who loaned us so many tools, and I don't think we returned them. Todd Billings, who kept us safe despite all our exuberance. Ray Sedgwick, who brought a real esprit de corps to the lab, both intellectually and community-wise. Javier De Luis, whose company impedance matched us to the professional world of spaceflight. Ed Crawley, who taught me a lot and taught me about how to wear steel-toed boots when chasing funding. That's a good lesson. Dan Hastings, who opened a lot of opportunities, taught me how to speak truth to power. Jeff Hoffman, for being Jeff. I remember he invited me several times to a private meeting to the commander of Apollo 15, Dave Scott. That's a rare event. You don't say no to that. And my wife, Mindy Morin, for putting up with me. And thank you all. And I successfully avoided Q&A, right? That's the goal. Sure. Any questions? Questions? Anyone have funding? No.
Dave, great talk and great history. As we're looking at the moon, I know we talked a little bit. Thank you. Al Tadros from Redwire, and class of '88. So as we're looking to go to the moon and create a permanent presence there, what experiments, what do students get to look forward to doing on the surface of the moon that we might not have been able to do on station or shuttle or other platforms? Have you thought about that and maybe your new role?
Well, my role at JPL, since we got there first, if everyone remembers the Ranger and Surveyor missions, had a little trouble doing it, but finally successful. I think there's some interesting challenges. Well, there's many challenges, but I think yours was more about the research question. But I'm going to mention one challenge. I believe we need Dave Scott here right now. When those landers, when the lunar modules landed, the blast ejected the dust at orbital escape velocity. So we got to think about what we're going to do to the orbit around the moon as we come in with even stronger rockets, and how much of that debris is going to get into space, and how do we deal with that or prevent it. Terrain relative navigation is a big thing for landing. They did it on Perseverance. But the lighting conditions on the moon are very challenging. So I'm doing the DC pivot. I'm answering the question I want to answer. So back to your question. I think a lot of it's going to be in the area of life sciences. So that's a great question for David Newman, who has left the room just in time. But, oh, she's back there, okay. You know, there's the quiet of the backside of the moon. You know, it's about the only radio silent spot in the vicinity of Earth now, and doing astrophysics, radio, or whatever out there, it would be great research against that sort of science. But the robotics of building that kind of telescope in a lunar crater is very interesting. The how to extract ISRU, you know, the water from the frozen, the sunless craters in the South Pole. I saw a great, I remember when I came back from NASA headquarters once, met with Ollie, and he showed me this work by one of your students, and it wasn't about how do you extract ISRU, it was about when is ISRU useful and buys itself into the architecture. I have found no one who has answered that question other than Ollie and his student. And I think that's going to be key into figuring this out. I'm out of time, sorry. Hope that helps. Thanks.